All right, so we talked about these. I'm going to go ahead and erase this because that was a unnecessary bird walk, overcomplicating it. And we figured out which one was longer using that. So here we have a rope on a string on a shelf. I think there's going to be a force of gravity. And perpendicular to the shelf, there's going to be a normal force. All right, for sure we have those two. And we're definitely going to have some sort of force going this way. So typically I get a question like, is there friction force too? And if it's being supported by the spring, then we usually leave the frictional force off. It's like the string is supporting all of that. All of the component of the weight, which is pulling it down the ramp, is being held by the string, I think is the assumption we make. So we'll just call that a tension. All right, this one is stuck on two shelves or something weird. So we have a force of gravity. And then we have a normal force coming off of this shelf. And we also have a normal force coming off of this shelf. Two normal forces. They actually could be equal. I drew them different sizes, not intentionally. They could be the same. Probably should be the same. Here we have a rock. And so what this is supposed to signify, I guess I forgot to tell you, was motion. These little hashy mark things are showing the rock sliding down the ramp. So there should be a normal force, perpendicular. And if there's the component of the gravity pulling it down the ramp, then that should be the component that's pulling it down the ramp, which is about yay much, should be balanced by, so if that's a centimeter, then the frictional force should be, so what, the equilibrium is just telling you how big to make the friction force, that it should be the same as the component of the gravity force that's pulling it down the ramp. All right, so we have those three forces. If you didn't draw it that way, it's okay. As long as you have the arrows pointed in the right directions with the right labels, you can get 100. All right, we have a rock that's falling. There's only one force acting on it, and that is the force of gravity, also known as the weight. Number 11, we have a rock sliding on a frictionless surface. So basically, we have a force of gravity, and we have a normal force, and that's it. What happened was 10,000 years ago, somebody kicked this rock on this infinite frictionless surface, and it's just been skittering ever since, because there's no force to stop it. First law. Right? There's constant speed. Constant speed means net force is zero, because acceleration, constant speed means A equals 0, which means net force equals 0. So these are balanced in equilibrium. There aren't any other forces. Now we have a rock falling at a constant terminal velocity. So this is a little different. We're going to have our ubiquitous force of gravity, or the weight. But now, since it's at a constant velocity, if the velocity is not changing, then the acceleration is 0, which means the net force is equal to 0, which means there has to be something balancing the force of gravity. So there must be an upward force pushing on the rock, and we're going to call that drag. What a drag. You could call it friction, and I wouldn't mark it wrong, because that's what it is. But it's a special kind of friction called drag. What a drag. All right, the rock is decelerating because of kinetic friction. So again, anytime something's on a table that's level, we basically have equal force of gravity, normal force every single time. And now, instead of, so now this rock that's been sliding for 10,000 years encounters a rough surface, and so now we have some friction over here, slowing it down. Anything I need to talk about so far? You getting them right? All right, so this is not a string attached to a rock. It's showing a trajectory, so I guess I should have said that. It's showing that the rock is going up and coming down. So the forces acting on the rock are force of gravity. Anything else? you could have a little drag force. It doesn't specifically say to worry about the drag force, but we just assume that it's in a vacuum if it doesn't say there's air resistance. So you could, I wouldn't mark it wrong if you drew a little air resistance pushing on the rock, like right there. It would have to be right there, though, because it's going up. So the air would be pushing down on it. Here we have the rock at the top of the trajectory. Now there's definitely only one force, and that's the weight. Questions about that? Did you get anything else? It's just stopping at the top and coming back. It's the force of gravity. Little g is the acceleration, right, caused by the force of gravity. We have a rock tied to a string and it's being pulled up. So here's the force of gravity, and now here's the pulling force, or the applied force. And the reason I made it longer is because if they were equal, if it was in free fall, the acceleration would be 9.8 down, and if they were in equilibrium, if they were equal to each other, the acceleration would be 0. It could still be moving with the 0 acceleration, it would be constant, but since the acceleration is up at 9.8, it means it's being pulled with a force twice as great as its weight. So I made this line twice as big as this line to be perfectly correct. All right, now we have a rock that's being pulled across the ground. It's taking my pet rock for a walk here. Force of gravity, normal force, friction. So there's an applied force here, or the pulling force. And again, yeah, I think it's just a good rule of thumb to say, if it's moving, we're going to call it pulling force or applied force, and when it's just hanging, we're going to call it a tension. I just made that up. You guys are the first people to ever witness me say that. I just figured it out after all these years. All right. Normal force, force of gravity. Whoops, don't forget the arrow. It's not right if there's not an arrow. Again, we have a pulling force. And so how this one is different is there's no friction. And this acceleration to 2g is just giving you a hint as to how long to draw the lines, but we're not grading how long the lines are. We're just grading the arrows and the labels. And that's it. That's the whole deal. We'll still have a few minutes for some blazer time, but not